Dear students, in this part of the lecture on cyclic groups, we will deal with two theorems. One is every cyclic group is abelian, and second one is every group of prime order is cyclic. Right. Before going to the actual proof of the theorems, let us recollect the examples. See here, the example 1 and 2 given here are cyclic groups, and suppose you take first group G is equal to 1 minus 1 I minus I. This group is generated by the element I. So we write G is equal to bracket I, or why we are writing G is equal to bracket I or the group G is generated by I? Because every element of G, you take any element A belongs to G, that can be obtained using some power of I. So I power n. Okay. For example, you want minus 1, you take I square. Suppose you want I itself, then what you have to take? I power 1. Okay. Like this. If you want minus I, you take I cube. So like this, right? Any element of G can be written as I power something because the group G is generated by I. Similarly, if see here, right, if the group G is generated by A, then any element of A can be written as A power something for some n belongs to J. Now, let us come to the first theorem, that is every cyclic group is abelian. Okay, let us start with a cyclic group. So, G comma dot be a cyclic group. So, what do you mean by, what is the definition of cyclic group? So, there exists some element in G which generates G. That means using A or powers of A, you can get every element of G. Right? That is what we write like this. And every element in G is an integral power of A. Okay? Because G is generated by the element A. Now, what is our claim? Our claim is to prove that G is abelian. What is the abelian property? So, if x and y are two elements in G, we have to prove that x dot y is equal to y dot x. That is the abelian property, right? Or commutative property. So, let us take two elements in G, and because x is in G and G is generated by A, x can be written as some power of A, that is A power m. Similarly, y, A power n for some m comma n are integers, right? Now, consider x dot y. So, what is x dot y? Clearly, that is equal to A power m into A power n, and by using law of integral exponents, A power m into A power n is nothing but A power m plus n, and m plus n and n plus m value is same because both m and n are integers. Add any two integers in any order, they give same result. So, A power m plus n can be written as A power n plus m, and this can be rewritten as A power n into A power m. And what is A power n? Is y, and A power m is x, therefore x dot y is equal to y dot x for all, and this is true for all x y belongs to G, therefore G is an abelian group. Hence, every cyclic group is abelian. Okay, very simple there. But immediately in mathematics we will have a question. What about its converse? What do you mean by converse? G is cyclic implies G is abelian. That is what we have proved. Okay, but do you guarantee the reverse condition? That means if G is abelian, then is G cyclic? Is G cyclic? Okay, that is the question. Okay, but that is not true always because we already have seen this example. Okay, here. So, if you see the introductory video on cyclic groups, I already explained why this is not a cyclic group, because every element, okay, is of order 2. That means, suppose you take B, except identity of course, take B, B power 1 is B, B square is A. Similarly, if you take C, C power 1 is C and C square is A again. Okay, D, D power 1 is D and D square is equal to A. So, that means each element generates that element and identity, nothing more than that. Therefore, this is not a cyclic group, but this group contains 4 elements. You know, we have a well-known theorem that if any group containing 4 or less elements, okay, then it is abelian. Therefore, G is also abelian, and it can be also shown here. Okay, using the composition table also you can show that this is abelian. See the composition table. Okay, in this composition table you can observe that it is symmetric. That is, first row is same as first column, second row is same as second column, third row is same as third column, and fourth row is same as fourth column. Therefore, this means that okay, G is abelian. But G is not a cyclic group. I already explained. So every cyclic group is abelian, but every abelian group need not be cyclic. Okay. Now we shall see second theorem, that is every group of prime matter is cyclic, or this can be also stated as if G is a group that contains, or the order of G is a prime number P, then G is cyclic, right? So to prove this theorem, let us start with a group G and whose order is a prime number P. Okay, obviously P is a prime, therefore P cannot be equal to 1. So if P is not equal to 1, you can easily say that G is not equal to E, because if G is E, that is if G contains only identity element, then what happens? Its order is 1 and 1 cannot be a prime. Therefore G has at least 2 elements. Therefore G has at least one non-identity element. That means at least one element A that is not an identity element, right? Now what I am taking is here H, which is a subset of G. Okay, I will tell you why. Generated by A. So let us see these examples. Okay, for example, when you take A is equal to -1, okay, generate a set. That means raise this -1 to different powers. Then it will give rise to a set H. What is this H? 1, -1. Similarly, when you take A is equal to 2, okay, then what is H? So it rises to, okay, if you rise these 2 to different powers or different multiples, then you got 0, 2, 4. This is H. Similarly, B, here you take B and it gives rise to some H. Okay, so H, and if you remember in the first video I told you that this becomes a subgroup. You can observe that this is a subgroup and called as cyclic subgroup. That is what exactly we do here. Now we consider a set H which is clearly a subset of G, because A is an element of G. A power n means A dot A dot A. By closure law, everything belongs to G. Therefore, each element of H is an element of G. Therefore, this is clearly a subset of G. Hope you understand. Now, what we will prove is that H will be a subgroup of G. That is the first part. So, to prove that H is a subgroup of G, okay, we use the following theorem. What is that theorem? Do you remember? The necessary and sufficient condition for a non-empty subset of group to be a subgroup is AB belongs to H implies A dot B inverse belongs to H. But first H should be non-empty, so that is why I wrote this first line. For n is equal to 1, A power n, because H contains all the powers of A. So for n is equal to 1, A power n is A power 1, that is A. Therefore A is an element of H, therefore H is not an empty set. Next, we'll prove this result. So let us take 2 elements in H. Before that, let us see this. If A belongs to G and G is a group, so A power n belongs to G and for all n belongs to G implies every element of H, that is A power n, is an element of G. Therefore H is subset of G. I already explained this here. Now, so let us take 2 elements of H. Okay, instead of AB, I have considered XY because already we have used A here. So XY. Now, again, X is, okay, some power of A, because what is H? After all, H is the set of all elements of powers of A. So if X is in H, X is also some power of A. Y is also some power of A. So X is equal to A power n, Y is equal to A power n. For some mn belongs to Z. Now what is X dot Y inverse? X dot Y inverse is A power m dot A power n whole inverse. So what is A power n whole inverse? Then A power m into A power n whole inverse can be written as A power minus n, and by using law of integral exponents, A power m into a power minus n is a power m minus n. And what is m minus n? If m and n are integers, m minus n is also an integer, right? So a power n integer, okay, is an element of H. Therefore, a power m minus n belongs to H. But what is a power m minus n? It is x dot y inverse. So x dot y inverse belongs to H. For it this is true if you take any x comma y belongs to H. Therefore, okay, by this theorem, okay, a known theorem in subgroups, H is a subgroup of G. And now we implement the Lagrange's theorem. So what Lagrange's theorem tells? If H is any subgroup of a finite group G, definitely order of H should divide order of G. So order of H should divide. What is order of G? P prime. So what are the divisors of prime number? Either 1 or prime number itself, right or not? So therefore order of H should be either 1 or order of H should be either P. But if order of H is equal to 1, what does it mean? It means that H should contain only one and only one element. So subgroup that contains one and only one element is nothing but singleton E. But this is not true. Why? Because H contains A. I already told you. Okay, when I prove that H is non-empty, I already show you that H contains, right, A. Right? See here. A is an element of H. Therefore, so, and one more thing, clearly I mentioned somewhere, A is not equal to E. Right? A is not equal to E. Therefore, H cannot be equal to E. Right or not? H cannot be equal to E, singleton E. Therefore, order of H should not be P1. So, it should be P. Means what? H is a subgroup of G or subset of G, and it contains, and H contains same number of elements as that of G. And G lo ఎన్ని elements ఉన్నాయో H లో కూడా ఎన్ని elements ఉన్నాయి. అర్థమవుతుందా? H is subset of G, and the number of elements in H is same number of elements in G. Therefore, definitely H should be equal to G. That means, what is H? H is a group generated by A. Now H is equal to G. That means G is also generated by A. Therefore, G is generated by a single element A. Hence, G is a cyclic group. Therefore, every group of prime order is cyclic. Right?